So now we're going to look at 7.2, confidence intervals for the mean when sigma is known. In 7.3, we're going to do it when sigma is not known. So here we are at 7.2. You're pulling out your formula card, calculator, paper, pen, sticky notes, index cards, whatever you need, just like you were in class, and even a combination of I'm at home and I can do a little bit more and spread out more. Got a lot of reading. Wish we were all together so that we could read this together. You can start and stop to soak in the information, but it starts something like this. In order to compute the confidence interval for the mean when sigma is known, keep this in mind, underline it, highlight it, think on it. There are two assumptions that must be met. Number one, that the sample is random, and number two, either our n, or sample size, is greater than 30, or the population is already normally distributed when it's less than 30. In this book, the assumptions will be stated in the exercises. However, when encountering statistics in other situations, you must check to see that these assumptions have been met before proceeding. Some of you are going to take more statistics classes. This is worth highlighting. Our class is a basic stats class, and everything's going to work out nice and pretty. So all of our information is going to be just fine. Some statistical techniques are called robust, and this means that the distribution of the variable can depart somewhat from normality, and valid conclusions can still be obtained. When you estimate a population mean, you should use the sample mean. You might ask, why are there measures of central tendency, such as the median and the mode, why they are not used to estimate the population mean? The reason is the means of samples vary. And I got a whole lot of writing going on up here. They vary less than other statistics, such as the medians and modes. When many samples are selected from the same population, therefore, I even wrote mic drop over here, therefore the sample mean is the best estimate of the population's mean. It's the winner. So now we're moving on. Remember, this section is, you can't see it. This section, I'm going to go back and make sure you see it. This section, it's confidence intervals for the mean when the sigma is known. You see a whole lot of writing here. Again, you can start and stop the video as you want. Right now, I would go here to your chapter 7, confidence intervals and sample size. And then right here it says Z, and then here it says T. I want you to write on Z that this is what we're going to use when the population standard deviation is known. Here, we don't know the population standard deviation, we know the sample standard deviation. So this is what we're about to use when we know sigma. And we're going to write a bunch of information on here that when sigma is known, we're going to call it a Z confidence interval. In the next section, we're going to be calling it something different because we won't know sigma, and we'll be calling it a T confidence interval. I've got a whole lot of bunch of junk written down here. They've written in several numbers, and I want to point out a few. Right here, notice I'm avoiding the formula because it looks nasty, and it is not. We're going to break that thing down very quickly. But here it says a 95% confidence interval, and it gives the number 1.96. I want to take us back very quickly to when we were playing around in the last section, and we were like, what are these numbers? But the 95%, you got to remember how we found all of this Z sub alpha over 2, and 95% turned out to be 1.96. Here we have our 99%, which was 2 and 5 5800ths, and the 99 turned out to be 2 and 5800ths. And so when you're looking here on your card, you notice there are none of those numbers. So somewhere on here, and you need to write it strategically so that you can read it and it makes sense and you know how to use it, but I would go ahead and write these numbers. That for 90%, you'll use 1.65. For 95%, you'll use 1.96, and I actually have about 7 written on here. For 99%, 2.58, 80%, 1.28, and these are all Z sub alpha over 2s. 98 will use 2.33, You may not be able to see that very well on the document camera. 2 33/100. 96% is 2.05, and 85 is 1 dot. That's not a negative. 4. So I would take a moment to even freeze the screen, take a screenshot, and get all of those written down very carefully in this area. Not sure how you want to write it there, but it needs to be something for you that you can understand and that you'll be able to use and recall in our work. This is a nasty looking formula, but who cares? If I break it down real fast, this much, you notice that is the mean of the sample. Oh, well, we've done that before. And then if you look right here, there is a sigma over a square root of the sample size. Oh, well, we've done that before too. Oh, look right here. There's a z sub alpha divided by 2 over 2. Oh, well, I know what those numbers are. Oh, so what you're saying is all I got to do is go find this thing right here. I'm going to take sigma divided by the square root of the sample, and then multiply it times that number for z sub alpha over 2, and I've got me a number. Yeah. And then we're going to do two things with that number. We're going to take our sample and subtract that number, and then we're going to take our sample and we're going to add that number. And we will be done, because that will give us the interval of which we are whatever percent sure that our actual population mean is between. That's it. That's all we're going to do. There's some more stuff in here that you do need to highlight and underline before we do an example. Like this term is called, I would highlight that, margin of error. Oh wait, it's also called maximum error of the estimate. I'd write all that down. For a specific value, say this, it's going to fall in between, and it's all like we just previously explained. But then they're going to talk to us a little bit about rounding. They're saying if we use raw data, round off to one more decimal place than the original data. So if the original data went to the tenths, then you round off to the hundredths, etc. But when you're computing a confidence interval and using the sample mean and the standard deviation, you already have the mean and a standard deviation, round off to the same number of decimal places. And when you use this in your jobs or in your future classes, you just need to follow their rules. What are they expecting you to do? Because they may want you to be more accurate. This is just a heads up. And then you also need to read the final directions of what are we asked to round to in Connect Math or on the test. So I've written a whole bunch of junk. I've got just a whole lot of stuff going on here. So here we go on our example, and then I'm going to ask you to do 7-2 by yourself. A researcher wishes to estimate the number of days it's going to take an automobile seller to sell a Chevrolet Aveo, or Aveo. A random sample of, and I would start marking, we got 50 cars, that is my N. Had a mean time on the dealer's lot of 54 days. Ding, 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 that's our X bar. Assume the population standard deviation to be, there's our population standard deviation. We have sigma. We're going to use a z-score. Find the best point of estimate. All of these things up here are raw data, well, not raw data, margin of error, maximum error of estimate, point estimate, of the population mean, and the, ding, 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 here's our confidence, the proportion for the percentage that we are asked to find for our confidence interval. And with that 95%, there's a number that goes with it. Well, that's what we wrote down up here. It's what we calculated in 7-1. But for 95%, we're going to use, for our z sub alpha over 2, we're going to use 1.96. Find it. Find the confidence interval for the population mean. So I'm going to cover up some of this just because it looks hideous. So the big things that you have to have narrowed down is that, oh wait, I had my sigma. Since I have sigma, I'm going to go use a z confidence interval. I can make myself a note when I have sigma. And I'm going to go write down this big old honking equation. So in your notes, I would write down the whole formula, and then I would go plug in pieces and parts at a time. 54, that's our mean. The minus comes from the formula. The 1.96 comes from that 95% where we're going to use adding on one side and subtracting on the other. 6 is our standard deviation, and 50 is our n. Less than, mu, less than, wash, rinse, repeat. 54 again, 196, this time it's adding. 6 in the numerator, square root of 50 in the denominator. And I'm just going to go pick on one of these, and I'm going to go grab my calculator. And when I grab my calculator, I like to outsmart the calculator, so I'm going to tell it, starting at the back, clear, 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 6 divided by, I'm going to have to outsmart this one, square root of, I think I did the square root, nope, I did a cube root or extra root, so 6 divided by square root of, 6 divided by square root of, 50, close that off and hit equals. So that's my 6 divided by square root of 50. I need to multiply it times 1.96 and hit equals. You don't have to do what I'm doing. You can plug it in straight, but I just go backwards and like to outsmart the calculator. So I think this magic number is 1.663. 1. Yeah, we'll go with that. 1.663. I know we had rounding rules, we had other stuff. So now on this far right side, I'm going to add that to 54. And I'm getting a number of about 55.6. That would be 7. Or 55.66. And again, it's going to depend. What do they want us to round to? Or are we following their suggestions? What is going on? So about 55.66. And when I look under here, right there, it says 55.7. Then I got to go over here. I'm going to take my 1.6631, and actually I'm going to say, I'll just go the other way. I'll do the 54 from over here minus, and I just want to make it a little bit more accurate, 1.6631 equals, and I'm getting a 52.34. And so here's my 52.3. So this is what I'm looking for us to be able to write. Can you write it with the parentheses as mentioned earlier? If you want to go this route, we need to subtract and divide by 2. We would take our 55 7/10 minus the minimum, 50.3. We get 3.4, cut it in half. And there's our 1.7. Then we still have to play around. Oh, I didn't need to do that. A long way to do that. All I have to do is to take my 54 and say I'm adding or subtracting that 1.7. Anyway we go, and then an additional, it would cover as low as 52 and as high as 56. Big thing is, do not freak out about this formula. Just attack it, put in the pieces and parts, do it carefully, and then look for how you're supposed to leave the answer. So right now, I would hit pause, and I would go do 7.2. Try to do it all by yourself. Like literally, cover all of this up, and you work on your answers, and then the answers are at the top of page 367. But for you and me, we're going to keep going. So you've cut the video off. You did this 7.2, and now you're going to join me at the top of 368, and we're right here at 7-3. It mentioned a while ago if we were just given information like, here is your mean, here is your standard deviation. But you look right here and we have raw data. And when we're given the raw data, they were saying to go out further, one more place on your rounding. And so we're going to kind of do this one lazy. On the 7.3, again, they have the following data. I should just read it. Represents a random sample of the assets in millions of dollars. This is important. Millions of dollars of 30, oops, there's my N, credit unions in southwestern Pennsylvania. Assume the population standard deviation. Sweet. They gave it to us. Then find the, and I'm going to play with this one for just a second just to help us remember what we did in 7-1, confidence interval of the mean. And so I already know it's 1.65. I've already looked at it over here. I already have all of this written on my card. I just want to take a minute to review this, even though it was just our last section. Oh, actually, last section. Yes. And so right here, the 90%, just a quick reminder that when you're looking at your curve and underneath the curve, they're saying they want a 90% confidence interval, what's going on from here to here. I just want to remind you all about the alpha, z sub alpha over 2. 90% when taken away from 100% leaves us with 10%. But that 10% is to be shared between the two tails. So one side is 5% and the other is 5%. And I told y'all I like to go ahead and go at it this route. Then I got a 90 and a 5, which is a 0.95. It's 95%. But I go ahead and throw in the extra 2 zeros so that when I go to my chart, my 0.95, it falls right here. And we have a rule that says if it falls exactly in between 2, you go with the larger. So I'm at 1.6, and if I roll all the way up to the top, I'm up here at 5. Again, that's what we already knew, but I wanted to take a moment to go back over that just one more time. We're going to pull lazy, and we're going to go to the X bar. We added all of these up. We divided by how many ever are there, 30. And then we found that the X bar, the mean of the sample is 11.091. And it says assume. So they're giving us some information. And we're going to go lazy for right now, for the sake of time, just like we were in class. Because my clock's ticking over there. It says find alpha divided by 2. And we've already played around this, we've already played around this, and we've got that it's 1.65. And then it mentions there's a more precise value, but we are going to use 1.65, and then we got this big old formula again, and we don't care because we're not afraid of it. For X bar, we're going to go put this mean that they found that we were too lazy to find. You're going to go put your z sub alpha over 2, which is our 1.65, which we either can say we found over here or that we used from our chart. Whatever we're going to say, we're going to put it right there. This is the standard deviation. We could have calculated it using some old skills of ours when we found the variance in the standard deviation. And then this 30, it's our n. I'm going to play around right here. I'm going to calculate that value. And I'm going to go ahead and say that's what I got, was the 4.339. And I put it on both sides, 4.339. One point I'm going to subtract it from my sample mean. And another point I'm going to add it. I get this range of values, and it says hence. One can be 90% confident that the population mean of all of these assets, of all of these credit unions, is between, and we got to bring back the million, 6.752 million and 15.430 million based on the sample of 30 credit unions. Just a little bit more to read, and remember, you can hit pause at any time and go back and look back over this. And at the top of 369 it says, when sigma is known, S can be used as an estimate of sigma, but a different distribution is used for the critical values, and hence that's going to bring us to our next section, and it's going to be when we start talking about this thing called T. And it's going to be explained in 7.3. I just want to use this last piece. And again, this is for everything you're doing and for anything you might do in the future. This chapter and subsequent chapters include examples using raw data. If you're using a computer or a calculator set of programs to find the solutions, the answers you get may vary. And the world is okay. And that is why I ask y'all to show work. And then when y'all are frustrated with a computer program on the homework, that's why I ask you to use Ask My Instructor. And it may vary from the ones given in the text. This is so because computers and calculators do not round and then round and then round and then round. They actually store all of this data inside. And they may use more exact critical values if we were plugging those in. When you are calculating other statistics, such as these that we're going to look at now and later, it is permissible to carry out the values of means, variances, and standard deviation to more decimal places. You are in control. I would not shorten the way you carry it out. I would lengthen it, like go to 3 or 4 decimal places, other than what's specified by the rules we were just looking at. This will give answers that are closer, they're going to be better, they're going to be more accurate, and these small discrepancies are just part of statistics. This concludes my part of the lesson on 7.2. There's going to be a video you're going to watch for the next part.